just use one factor. And it's not for the material, but it's for the action. So if it is bending strength, then it can be anywhere between 0.65 and 0.9 phi factor, which is strength reduction factor. If it is shear, we use 0.75, whereas in IS 456 we must use for concrete 0.446, and for steel 0.87. For FRP, what's the value? We don't have one, right? So just take a note of that, because that's in your quiz. Yeah, right. I mean, I don't know why, but it may have to do with the comment is we are over designing using IS 456. But the reason, maybe, I'm not sure, I'm guessing, it's because the quality control is not as stringent in Indian context. Because I worked in Engineers India Limited, I know exactly how things are done. Of course, that was a long time back, but but quality control is not as stringent as it is in other places. Okay, so that's the reason they may have that slightly over design, which is fine. Like in earthquake resistant design, the main objective or main goal in earthquake resistant design is what? Say that again. Ductility is correct, but why do you want additional ductility? I'm sorry? Damping is okay. That's we are talking about ductility. So what? Say that again. Yes, I agree with all that you are saying, but why do I need ductility in earthquake resistant design? There are two things. One is it gives you warning. So if you have very large deflections, you know that something is going on. So you run. Right? That's number one. Number two, the ductility will provide the ability to maintain the load carrying capacity under large deflections. That's the pure meaning of ductility. Ductility is the ability of a structure. Ductility of a structure is the ability of the structure to maintain the load carrying capacity under very large deflections. So the whole purpose is there is no collapse. It can have very large cracking, very large deflections. You may have to tear down the structure and build it again, but the structure itself should not fall over or it should not collapse. That's the whole point of earthquake resistant design. But anyway, we are deviating from our discussion. So these, I just have this side by side. 1.5 dead load, this is for IS 456, that's for ACI 318. So U equals 1.5 dead load plus 1.5 live load, whereas here we use 1.2 dead load, 1.6 live load. So for just an example, generally speaking, dead load to live load ratio is 1:1, is kind of okay for concrete structures. So if we say the ratio of dead load to live load is 1, so I took dead load 100 kilonewtons, live load 100 kilonewtons. So IS 456 will give me 300 kips or kilonewtons, sorry, kilonewtons of load, and ACI will give you 280 kilonewtons. So you are actually designing it for a smaller load using ACI. Okay, so that's on the loading side of the equation. And on the strength side of the equation, of course, there is a gain. There is a difference. The difference is the concrete strength. Of course, some of it is due to cube strength. Some of it is. Whereas in IS 456 we use 4.446 sigma CK, which is the characteristic strength. For steel you use again 0.87 sigma Y or Fy. Whereas in case of ACI we use factors related to the action. So bending is an action, it's not a material. So we use 0.65 to 0.9. So more ductile the design is. You want to use 0.65 for ductile design or 0.9? So that may be a trick question. If you are expecting brittle failure, you use a smaller strength reduction factor because that will give you larger reserve strength. Does it make sense? We are going to use this concept in our FRP design as well. If you are using very lightly reinforced, that means under reinforced, very lightly reinforced section, then you will have very large ductility. Therefore, you can use a larger strength reduction factor. That means we are utilizing larger design strength. Okay, that's what is the basis for this 0.65 to 0.9. So generally speaking, over reinforced sections or balanced sections, which are not allowed in actual design, but balanced section you must use 0.65. For under reinforced sections, which can give you minimum of strain of 0.005 in steel, use phi factor of 0.9. Does anyone remember what the corresponding strain is in IS 456? When do you classify a section to be very ductile in IS 456? Does anyone remember that? I think there is an equation which says Fyt over 1.15 ES plus 0.002. Do you remember this? Yes. So this is compatible to tension control section. Compatible. So if I use, let's say, Fyt is 415 and this is 1.15 and this is 200 GPa, right, plus 0.002. This will probably work out to be around 0.002 divided by 0.1. It's probably 0.0017 or 18, something like that, plus 0.002. So this will work out to be 0.0038. Okay, so that's a little bit lower than what ACI requires. ACI requires the minimum strain to consider it to be a ductile member is 0.04. Sorry. Okay, so we'll come back to this in a minute. So if you have very good ductility, use a larger strength reduction factor. And then for shear, it's 0.75. So in FRP, what we will do is, we are not too comfortable using FRP in aggressive environment. So what we do is we reduce the guaranteed tensile strength by a small amount. And that reduction is achieved with C sub E, which is known as environmental reduction factor. Okay, this is something it's useful to remember. Depending on the exposure condition, we'll reduce the guaranteed tensile strength. Guaranteed tensile strength is based on what? Do you remember? I'm sorry? Remember guaranteed tensile strength? So guaranteed tensile strength, let's say FU star is equal to average strength FF average and minus 3 sigma. So any average strength you get, you take away or deduct 3 times the standard deviation for that set of tests, and that's your guaranteed strength. So on this guaranteed strength, we are adding one more factor. We are adding, because of environmental condition, we are adding one more factor to this. Okay, so that's what we are going to do. In FRP design, we are going to add one more factor for on guaranteed strength. So for strain also, we will use strain as a basis for design in FRP. In case of steel design, we don't normally use strain as a basis except for earthquake resistant design. only in earthquake resistant design you talk about strains, strain based designs. But in case of FRP, we will use strains in some designs where we limit the maximum strain to certain amount. That certain amount is epsilon FU. What is epsilon FU? It is the design. That one was guaranteed. With a star, it's guaranteed when you add, when you have your CE, that's your design rupture strain. So design strain is with C sub E. In case of modulus, we don't use any C sub E. Okay? No reduction for modulus. Because we already use that in strain, we already use that in tensile strength. Therefore, you don't want to use another CE on modulus. Okay? No reduction. And you should not try to use FRP bars where the operating temperature, service temperature is greater than the glass transition temperature. What is glass transition temperature? Does anyone remember? It becomes soft. Yeah. In simple terms, the matrix becomes soft at that temperature. So you don't want to use that. Okay. So what is C sub E? C sub E is given in this table, table 6.2, and for different fiber types and for different exposure conditions, we have different CE factors. So carbon is very reliable. It doesn't get affected too much by environment. Therefore, if the concrete is not exposed to earth or weather, that means interior conditions, then we can use C sub E of 1. For glass, it's 0.8. For aramid, it's 0.9. However, if concrete is exposed to earth and weather, which is including moisture, then for carbon also we must use a small reduction, that is 10% reduction, which means 0.9 factor. Glass, it's 0.7, slightly less than 0.8. For aramid, it's 0.8, slightly less than 0.9. Okay? So these are the CE factors. Now, if you have bends, so we need to fabricate our ties and stuff like that in bent condition. So if you see straight bar, the fibers are aligned in the straight line, right? So they will be okay. You have load transfer in a straight line. But if you have bends, the strength of the bend is smaller than straight bar. And how much is it smaller? By a lot, actually. So they give you an equation for strength of bent bars, not bent in the sense you don't bend it after you fabricate. If you do that, it will break. You fabricate as a bent bar. And even for that, because the fiber is changing direction and you have, the change in direction and some kind of stress concentrations in the bend, depending on the radius of the bend, you need to use a smaller strength for stirrups. Okay? You have to remember that, or at least make a note of it. So you cannot use 100% strength in case of shear design. We'll talk about it tomorrow. Shear is for tomorrow. So in case of bends, let's say standard bend radius is maybe inner diameter or inner radius is about 2.5 dB for steel, right? Do you agree with me? I don't know if you remember that. But if you are detailing, that's what you do, right? The bend diameter is about 2.5 times the diameter of the bar, the inner one. So the average is, this is average radius, RB, diameter is 5 times. So radius is 2.5. So 2.5 plus half, that's about 3. 3 times dB is very common. But for FRP, you might want to have a bigger radius, because bigger radius will give you better utilization of strength. So you just plug in the numbers, and then you have for FFB equals 0.05 RB over dB, that's a ratio. So this equation takes the same units as FFU. So even if you use MPa units, it will come out to be the same. So for a bend radius of 2.5 dB, the reduced strength, this will give you reduced strength. So the reduced strength is 42.5%, and therefore reduction is 57.5%. And if you use 5 dB as your radius to the center line of the bend, in that case the reduced strength is 55% and the reduction is 45%. Okay, that's what we will use. So now we'll switch to the next PowerPoint, which is the next day 3 PowerPoints. So we are behind by at least 40 minutes or 45 minutes, but we'll try to make up. So in this presentation, I'll present the fluxural design basics. Some of you can go back to sleep, no problem, because you know this really well, right? Don't worry. But I'll wake you up when I'm talking about ACI, because that may be slightly new to some of you. Okay, so don't mind the repetition. So IS 456. So this is our standard beam. You apply load, you get your strain diagram. We are very familiar with this. We can do this even in the middle of the night. Like you're sleeping, somebody wakes you up, draw the strain diagram, you can draw it. Draw the stress diagram, you can draw it, because we know this reasonably well. So the strain diagram is very, very important to us. So everything depends on strains. Okay, the stress block is a result of strain diagram, but strain diagram is the most important diagram in any section analysis. So the actual strain diagram, this is one of the assumptions. The plane section assumption gives us linear strain diagram. In some cases it may not be linear, particularly for deep beams, that may not be linear strain diagram. But for normal beams, we have linear strain diagram. The stress diagram should look like this. For concrete, above the neutral axis, we have compression, and this is a parabolic stress strain curve, right? In IS 456, we don't use parabolic stress strain curve. We use something else. We'll come to that in a minute. So this is Fy. Fy is only at the level of the steel, which is very straightforward. We know this really well, so we'll move on. This is what we have in IS 456. What do we have? We have stress strain diagram, which is actually it should have a falling branch here, but this approximation simplifies our analysis. So they just make it a straight line. So up to 0.002 you have parabolic variation. Beyond 0.002 up to 0.0035 it is a linear or constant stress for any strain between 0.002 and 0.0035. That's another difference. In ACI we use the strain to be 0.003, whereas Europeans and British standards, Indian standards use 0.0035. Australian standards use even higher. But if you do any strain compatibility analysis, it won't make any difference in the actual strength calculations. Moment strength will be about the same. What about steel? Steel is normally bilinear stress strain curve. That's at least our assumption. We assume that we will have bilinear, that means two lines in our stress strain diagram for steel. So this is what it looks like. So the actual stress strain diagram, we have strain on the x-axis, stress on the y-axis. We have the slope here, the initial slope, that's our modulus, and then we have a peak, and we assume in all the codes, standards, the assumption is the peak stress is achieved at 0.002. That's irrespective of what code you use, you will see that. So that's the basis for your compressive strength design. For any compression member you are designing, our basis is 0.002. However, for beams, we can utilize a larger strain, which is 0.035 in case of IS 456. In case of ACI, it's 0.003. Very simple stress strain diagram. There are many equations. Some of you are familiar with that because I think yesterday somebody was mentioning some stress strain diagrams which will define the shape of this stress strain diagram. Ideally you should use calculus, integrate it, and then get your total force. But who has time to do all this in a regular design? Therefore ACI and of course IS 456, they all simplify this into a simple stress block or stress diagram. So up to 0.002 we have parabolic variation. Between 0.002 and 0.0035 it's a constant stress. So these two stress blocks will give us the complete representation of stress strain curve all the way up to 0.0035 in case of IS 456. But this you all know really well. So this is the actual stress strain diagram, parabolic one, and the idealized stress strain diagram is this for IS 456. All that they have done is they found out the total area of this under the curve of these two blocks, and they tell you that's 0.36 FCKXU, where XU is the neutral axis, depth to neutral axis from here to here, and then the maximum stress is 0.444 FCK. Okay, just remember, of course you probably remember it already, but try to remember this. I'll ask what this value is later. And the total value is 0.36 FCKXU, and the distance from here to here where the resultant acts is 0.42 XU. So that's another thing we need to at least come back to later. The total tension in the on the tension side is 0.85 Fy. That's the stress, average stress we assume in steel, and then AST is the area of steel. Very simple stuff. We know this really well. So I just have the same thing in 3 dimensions, but it's not needed because most of you teach these, so you really know it very well. Okay, let's move on. Now the movement strength can be based on the total compressive force, which is the area of the stress block. In case of IS 456, the area works out to be 0.36 FCK XU times B for a rectangular section, right, with a width of B. Very simple. What about the total tension? 0.87 Fy, that's the average stress times area of steel, AST. Then once you establish equilibrium, C equals T, and that will give you this equation here, XU equals 0.87 Fy AST over 0.36 FCKB. That's what I think is given in IS 456. But you can simplify it further and you can say that's equal to 2.42 AST over BD times Fy times over FCK times D. The advantage of this is we have ratios, so we'll reduce the units to just D. So 2.42 times rho is the steel ratio Fy over FCK times D. And then you have moment strength is based on the moment arm, which is D minus 0.42 XU, that's by IS 456, and then T is the total tensile force. So you know this really well. We will derive, or at least go over some of the similar equations in ACI, so that you get just a feel for what the equations are, and then you can use ACI 440.1. The whole point is that's where we are headed. That's my ultimate goal. I want you to learn how to, or I want to present the design methods by ACI 440.1. So in case of IS 456, you have a simple example here. If your width is 250 millimeter, overall height is 350 millimeter, effective depth 310, FCK 25 MPa, Fy 415, 3 number 12s will give you 339 square inches, beam span 5 meters, self weight including other dead loads 3.7 kilonewton per meter, and then live load 3.75 kilonewton per meter. So we'll try to find out the moment strength for the beam design and factored moment for the beam design and moment strength. Probably you already done the calculation. You are so familiar, you can probably do mentally. Done. But these are the calculations. What we get here is we will get a WU, which is factored load, uniform factored load. If there are any mistakes, please let me know, because there can be mistakes. I don't know. Sometimes I trick my students. I just have deliberately I'll have 1 or 2 mistakes. If they don't pay attention, they will not pick it up. And another trick I play is in the class when I'm teaching, I make a lot of mistakes. Then they say, for every mistake you find out, I'll give you 1 extra point, extra mark, okay? So my standard joke is, these days, I was able to do that when I was younger, but these days if I give that to you, then you'll all get 100%, so don't do that. So, meant to be a joke. You have to laugh. So anyway, so you have to keep everybody awake, right? It's very hard. 4 hours of, and most of us who are teaching, we are more used to being here and teaching. You are not used to sitting there and listening to my, lectures for 4 hours, right? So I'm sorry, but you can blame Dr. Das for making you do that. So the total compressive force will work out to be, okay, before that we have this factor load moment, which is 34.92 kilonewton meter. And you can get your XU 54.4 and the total compressive force 122. I like to work it this way. I like to find out each and every item, and then it's all in front of me, the total compression, total tension, and then movement based on moment arm. That's what I would like to do. Many textbooks, they give you one final formula, say use this formula. Formula wise, it's not good. This is, in my view, it's a better way. So you see step by step, you see every single item, and then use those items. That's what I do. So C is 122.4. I just verify that my tension is also 122.4 kilonewtons. Get my moment strength 35.15. It's designed very closely. So I'm trying to maintain 1 here. So moment strength